Okay, great. So this is the second course on probabilistic programming. I was trying to think how to position it with respect to Andy's course, which I hope you all enjoyed. I wasn't here, but I enjoyed watching the videos that are already online. And I thought maybe, I haven't run it by Andy, but I think this is fair. I think Andy was talking about reality, like the real state of the art, how things can work for a large number of people. I want to talk more about a dream of where things could go with probabilistic programming. So probabilistic programming is about statistical modeling, and that might have implications for science, for social science, for machine learning. And I want to talk about where a very general probabilistic programming language could take us. And to do that, we'll need to look at the foundations of probability and statistics, as well as the foundations of programming. That's going to take us to something which is called non-parametric statistics. I'll explain what that means when we get there. Okay. So it's a dream, but it's not to say you can't, that it's not real to some extent, and there are little languages that you can play with, and there's a system I've made you can download and try during this course. Okay, but it's just not, certainly nowhere near as plush as the systems that Andy was showing, like Staton, like the Excel add-ins. Okay, so I want to start by talking about statistics, and in particular Bayesian statistics. Everything in this course is going to be about Bayesian statistics. So who can remember Bayes' law? Okay, right, so like 60%? Does someone want to tell me Bayes' law? Because it's not just an existence proof.
A given B equals A and B over A P of B.
Yeah, okay, yeah. In slightly different formulation, somebody? Okay, so sort of, oh, yep.
A given B equals A and B times P over A?
Yeah, something like it, okay. So let me write it in words. But how far up can I go here? Can I write here?
Yes.
I'm going to use the screen again in about 2 minutes. Okay, so I can write here, can I? Down a bit? Yep. The camera says it's okay. So in words, I would say Bayes' law says the posterior probability is proportional to the likelihood multiplied by the prior. Okay? So these are words. The prior is my belief before I start doing anything. The likelihood is how likely the data is given something from my belief. And the posterior is what my belief should be when I've updated it with the data, with the observations that I'm going to make. So now let me write it maybe in how you've seen it in school. The probability of X given D, where D is the data, is, let's say, equal to the likelihood of the data multiplied by the prior. And now it's not equal, the posterior probability is not equal to this product, but rather it's proportional to it, so we need to divide by a normalizing constant. So as one of you said, the normalizing constant could be the probability of the data, but actually that's equal to something which is more useful to think about, which is the sum of all of these things. So in a finite case, that might just be a big sum. If you don't worry about integration, it's just a big sum. But in the general case, it will be an integration. Okay. So the difficult thing about Bayesian statistics, especially as far as simulation is concerned, is calculating this big sum. This is calculating a big integral, which is a very expensive thing to do. Okay, so that's Bayes' law. Let me take off for now this formal. I'll just write. So probabilistic programming for me, probabilistic programming, is given by adding to a normal programming language. By normal, I mean conventional programming. 3 things, and the 3 things correspond to the 3 clauses in Bayes' law. First of all, start at this end. A way of drawing things from a prior. I'm going to call that sampling. Secondly, a way of incorporating observations. Sometimes going to call that scoring. I'll explain why. And thirdly, a way of finding the posterior. So the idea is to specify a statistical model by writing a program in a fairly powerful programming language or a weak programming language, depending on where you want to sit, and adding to it sampling, observing, so those two things from base law, and then finding a posterior, which amounts to finding this normalizing constant. So I don't know, let's call that, I've used the word normal twice, normalize, might be called simulate. It's got different names. It's sometimes called run query, and so on. Okay. So that's probabilistic programming in a kind of a slogan. Now let me look at an example. Now I said I wanted to have a dream, but actually I'm going to cut down to a really, really simple example to start with so that we can sort of all understand what we're talking about. And this is an example of a probabilistic program that uses these three constructions, but it only uses each one once, just to keep it simple. So let me tell you a little statistical story. It's not a true story, but perhaps it's fairly... Yeah. So I've forgotten what day it is. As I said, I haven't actually forgotten what day it is, but suppose I've forgotten what day it is. I look out my window, and I see 4 buses go past. Now, I've got an idea that at the weekend, there are usually 3 buses per hour going past. And on a weekday, there are usually 10 buses per hour. So the buses are more regular in the week than they are at the weekend. I see 4 buses. Is it the weekend or not? So a statistician would write this as something like this. My prior belief is that x. So x is going to be whether or not it's the weekend. It's distributed as a Bernoulli probability. Like the 7 days in the week, 2 of them are weekend days. And a Bernoulli probability is just a fancy word for a coin toss. It's either true or false that it's the weekend, and my prior belief is that there's 2/7 chance that it's the weekend, 5/7 chance that it's not the weekend. Okay, just corresponding to the 5 days of the week. My likelihood, now I observe those 4 buses going past, and my likelihood's going to depend on whether it's the weekend or not, because there are more buses going past in the week than there are at the weekend. So if x is true, then my likelihood is the probability that 4 comes from a Poisson distribution with rate 3. So x means weekend, by the way, let me write that. So Poisson distribution, who remembers what a Poisson distribution is? 1, 3 or 4, slowly kind of coming back. Okay, so a Poisson distribution, well, one way I like to think of it, well, I think the best way to think of it is in terms of a Poisson process. So a Poisson process is a random collection of points. And those points are independent. So it's a random collection of independent points. So if we think of buses coming, let's imagine that this is a city without a bus timetable. It's just that we're told buses go 3 times hourly or 10 times hourly. And let's imagine that there's no synchronization, there's no traffic lights or anything like that. So buses come on average 3 times an hour or on average 10 times an hour. And so there might be more or less than 10 or 3 buses per hour, but they will come independently. On average, there will be 3 buses in an hour or 10 buses in an hour. And then the number of buses that come is distributed as a Poisson distribution with the rate, given that that's given either 3 or 10. Okay. So if it's not the weekend, then I still observed 4. My data point's the same. I observed 4 buses, but coming from a Poisson distribution with rate 10. Okay? And now I want to know what's the posterior. So this is informal notation. Statisticians use this tilde thing, which is sometimes precise and other times a little bit vague. Now I'm going to write it as a probabilistic program, this specification as a probabilistic program. And this is a program that I'm going to, if I don't make any mistakes, I'm going to write it in a syntax that you can then run immediately inside the system that you can download. Okay. So I write down my prior like this. It's 2/7 chance that it's the weekend. And then I can use a programming language construct to do this if then else, rather than informal English. Where are we? Then 3, else 10. And then observe 4 from a Poisson distribution with rate with the given rate. Okay, and now I've got this nearly defines my program. Then I want to return x because I want to return the thing that's interesting to me, which is whether or not it's the weekend. So this describes a program. I've used the prior and I've used some likelihood information. I haven't yet said I want to find a posterior. Actually, in all the examples I'm going to give today, I find the posterior at the end. So I'm going to say normalize at the end. Okay. Some probabilistic programming languages, it's useful to nest these queries, and that's quite interesting to do. But in many situations, you just find a posterior at the end of the story. Okay, let me show you then a picture of the Poisson distribution. There we go. That's good. Okay, so Poisson distribution looks like pointer. Okay, looks like this. So sorry if you can't see red and blue. It doesn't matter. When the rate is 3, you see it's most likely to be around 3, but it could be more or less. And it goes on, the support is infinite. Could be any number in principle. When the rate is 10, you see it's a lot more spread out, and the average is around 10. So now we can use that to calculate what this program does. So what I'm going to do is I'm going to calculate what this program does, and then we'll talk a bit about motivation, and then we'll come back and make this program a bit more interesting. It's a I said I had a dream, a very, very simple program. Very, very simple program. Let's look at how we can make it more interesting. But first, let's talk about what it does. I think I'll do that. Let me number the lines of the program. Line 1, line 2, line 3, and line 4. Okay. So I'm going to show you 3 ways of understanding what this program does. The first way is just a direct calculation based on what you would do in high school. I don't know about you, I learned a little bit about statistics in high school. I had to memorize the formula for the Poisson distribution and stuff like that. And I think I would have been able to answer this question to say, what's the posterior probability that it's the weekend? So we can do that. Let's look at how you do it. So the posterior is proportional to the likelihood and the prior. And that depends, right? So in the case when it's the weekend, the likelihood is around, can I point with my finger? The likelihood is the probability of the observation, which is 4, coming from the Poisson distribution. So when the rate is 3, we see the likelihood is around 0.1, I've got it written down here somewhere, 0.17, okay? The blue line hits the 4 stroke at 0.17. So the likelihood, the posterior, is proportional to the likelihood, which is 0.17, times the prior, which is 2 out of 7. And a quick calculation, this is about 0.05, I think. This is approximate. Okay. And this is also approximate. That's the product of likelihood times prior. If x is not true, then what's the likelihood? Well, it's much lower. It's where the number 4 crosses... there we go, thanks. It's where the number 4 crosses the red line, which is, I've got it written down here, 0.02. And the prior, so we're looking at the likelihood times the prior is 5/7. And that's approximately 0.01. Now what we want to know is what's the posterior probability that it's the weekend. Can anyone finish my calculation for me? So this is the sort of unnormalized probability that it's the weekend. This is the sort of unnormalized probability that it's not the weekend. These numbers don't sum to 1, so they're not probability distributions. Yeah. You're right, I want to sum them because I want to find my normalizing constant. But I'm not ultimately that interested in my normalizing constant. I'm more interested in the actual probability. Okay. So the normalizing constant is 0.06. What's the probability? 5 out of 6, exactly. Yeah. So posterior probability of it being a weekend is about 5 out of 6. So I ran my program with a simulation, and this is what it gave me, which is about 5 out of 6%, 5 out of 6 chance that it is the weekend. Okay. So that's the first way to understand the program, is to just do a direct calculation. And there are some, just a sec, there are some computer algebra systems, some probabilistic programming languages that link up with computer algebra systems and would do this kind of calculation for you, maybe if everything's in a closed form. Things like Hackaroo, which was developed in Indiana, and something developed in ETH Zurich, which I've forgotten just now. Psi, that's right, thanks, yeah. Sorry, you had a question? Sorry? Right. So the posterior probability that's the week, I'm not sure if this is what you're asking. But posterior probability that's the weekend is 5 over 6. The posterior probability that it's a weekday is 0.01 over some of these things, which is 0.06, which is 1 out of 6. So this, the reason I'm writing 5 out of 6 is because that's 0.05 over 0.05 plus 0.01. Does that help? Okay. Or maybe you're making a joke because I've written approximate and we want to know how confident am I that it's approximate. Yeah, that's an interesting idea. Let's not go there. Okay. That's my first method of running these things. But let's look at another method, which is a simulation method. So I don't know if some of you know the idea of a definitional interpreter. Anybody seen definitional interpreters? So a couple of people. John Reynolds had the idea maybe 50 years ago. This has nothing to do with probabilistic programming. John Reynolds had the idea maybe 50 years ago of describing programming languages by giving an interpreter for them. But it should be a definitional interpreter, not like a fast interpreter. So a definitional interpreter should be clearly written, not necessarily efficient or optimal or anything like that. So what I'm going to do now is not a definitional interpreter quite, but I'm going to give a sort of a reference semantics for programs like this. It's not the fastest one. We'll talk a bit more about that tomorrow, but it is a kind of a reference implementation. So let me just add that as well as definitional interpreters, as Reynolds suggested, another method of explaining what programs do is denotational semantics, proposed around a similar time, maybe a little bit earlier, by Dana Scott and Christopher Strachey. And the idea there is to describe what a program does by using a mathematical object, rather than as an interpreter giving a mathematical object. And that's what we'll do tomorrow as well. Okay, so that's my first way of running a program. So that's A, let's call it direct calculation. Okay. The second way I'm going to run programs then is by simulation algorithm. I'm going to show you two simulation algorithms. This one I'm going to call Monte Carlo with rejection. Okay. I'm not sure did Andy show you rejection sampling? Very briefly. Okay. So let's look at that. So the rough idea of a Monte Carlo method is that we're going to run our program many, many times. We're not just going to run it once. It's written as a program that usually you run programs once. We're going to run it many times, maybe 1,000,000 times. And we're going to look at what happens each time we run it. Each time we run it, we're going to make random choices. Okay. So we run the program, let's say k times, where k is a big number. On line 1, we actually toss a coin. We don't actually toss a coin. We actually make a random choice well, with 2/7 probability, we're going to say true, and 5/7 probability, we're going to say false. You might do that by generating a random number in a unit interval using some random number generator, and then seeing whether what you get is less than 2/7 or not. So generate, also let's say sample from Bernoulli. We toss a coin. Okay. We keep running through the program. We know how to do this. It's just an if-then else. Then we need to record an observation. Well, in rejection sampling, what you do is you draw from a Poisson distribution. I like to think of this, if you want to think of a Monte Carlo method as a simulation, let's simulate the whole bus network. Now, when we simulate the whole bus, and then see how many buses we would get in an hour according to that simulation. Now, when you simulate the whole bus network, buses are coming, let's say, independently, then the number of buses that come will be Poisson distributed with a given rate. So we may as well shortcut that. I mean, you could just write a bus network simulator if you wanted, but really I think at line 3, we sample, let's say, n from a Poisson with the given rate, which will be either 3 or 10. And then, so we've got our n. N doesn't appear in the program. But we have observed 4 from a Poisson in the program. So if n equals 4, we're okay. But what if the bus network simulator didn't come back with 4 buses in the given hour? Something's gone wrong, and so we reject that run. Stop. Or you can keep going if you want, but we're going to throw it away in the end. Okay. And then in the end, when we run this, we're going to get quite a few traces rejected, quite a lot of runs rejected. But of all the ones that we accept, so we have these accepted answers. Let's call them x1 up to, well, it's not going to be xk, is it? It's going to be something else. What comes after kl? It's good because we've rejected some of them. Okay, so L is less than K. So we've got these things, x1 up to xk. And we can then look at the ratio. These are going to be true or false. They're going to tell us, is it the weekend or not in each run of the program, in each simulation. And then we want to look at, of all of these results, how many say it was the weekend, how many say it wasn't. So the posterior probability that it is the weekend, well, an approximation to it, an empirical approximation to it, is the size of the number of things where we got true back divided by the total number of accepted runs. Okay, so we'll, on average, so as let's say k or l, as k goes to infinity, this goes to 5/6. Okay. So as we look at more and more k, we'll end up always getting 5 true accepted runs for every 6 accepted runs. Okay? So we run the program, we reject all the runs that don't match our observation, and then we count what proportion were okay. One subtlety that maybe we'll return to tomorrow is that when we run the program, this isn't a deterministic answer. We run it for, let's say, 1 million steps. We're going to get back a ratio here, but it's not a deterministic answer, because when we ran the program, we used some randomness, maybe from a system random number generator, maybe some quantum mechanics or whatever. And so we're going to get a different number each time. But as k goes to infinity, this is kind of the law of large numbers, the result, no matter what random number sequence we start with, goes to 5/6. Let's put that at the top, and then let's talk about the third method. I should do it over here, which is also a Monte Carlo method. But it's a variation on this rejection sampling. So this rejection sampling is really inefficient. You end up throwing a lot of stuff away. But we're not talking about efficiency now. But it's also not good because it doesn't always work. We'll talk about that in a minute. Let's look at our third method. And I'm going to call that weighted Monte Carlo. It's sometimes called importance sampling Monte Carlo. It's quite similar, except we deal with the observations differently. So we're going to run the program k times again. When we see something from the prior, a sample, we make the sample. So at line 1, we sample from Bernoulli. We toss a coin, or however we're going to do it. Line 2 is straightforward. It's just a traditional programming language thing. At line 3, we no longer simulate the bus network. Rather, we weight our run by the value of the density function, by the likelihood. So the value of the density of the mass function at the point 4, which, what did I say it was? It's either 0.17 or 0.02. 0.02 here, 0.17. It's called a likelihood. Now, it looks like a probability for now, but when we move to the continuous case, likelihoods and probabilities are subtly different concepts. So weight the run by the likelihood of the data. And the data point is 4, so we're going to weight the run by either 0.17 if x is true, and 0.02 if x is false. And we get that because we know a formula for the likelihood of the Poisson distribution. And now at the end of the day, we end up not with a sequence of results, but a sequence of weighted results. So we get a sequence of pairs, x1, w1, all the way up to xk, wk. So we have a result which is a Boolean, telling us whether it's the weekend or not on that particular simulation, and a weight which will be either, in this case, very simple, either 0.17 or 0.02. In general, the weight might be something more crazy than that. And now how do we find out the posterior probability? Well, what we can do is take the sum over all, we want to find out posterior probability that it's true, let's say, that it is the weekend. So we could take the sum over all i's such that xi is true, all the traces where xi is true, of the weight. So we look at the overall weight of true traces, and we divide that by the overall weight across all the traces. So our normalizing constant now, this thing here, is the sum of all the weights, and but the probability that it's true will be the sum of all the weights of the traces where we got true out. Okay. So this, as k goes to infinity, this goes to 5/6, which is the posterior probability that it is true. Again, each time we run it, we're going to get back a slightly different ratio, but as k gets bigger and bigger, we're going to, more and more of the time, get something like 5/6.
You know how you said either 0.17?
Yeah.
Is that supposed to be 0.2 or
0? Yeah. Okay, so it is the 0.02 is the number that, okay, which is the likelihood of seeing 4 buses in a given hour when the rate of buses is 10. It's quite unlikely that you would only see 4 if on average there are 10 buses per hour. Was there another question? It was also about this extremely technical point. Okay, so before we make it more interesting, let me say a few words of sort of general words. Okay. So some of my reasons for studying probabilistic programming. So one reason is we can move from the informal statistician's notation at the top here to a formal, precise specification like the program that we've written here. And moreover, we can start to understand what it means. And now, typically you wouldn't write a model that was 4 lines long that you could have solved when you were in high school in a 5-minute exam. You'd have a program that's 100 lines long. And we want to understand what bits of it mean. Typical compiler writer things to do, moving bits of programs around, understanding whether that's okay, and so on. We want to understand what that involves. Secondly, this is a simple model, but we can start to make it more interesting. I'll do that in a second. And I want to understand to what extent can we make models more interesting? What's the real landscape of statistical models? Statisticians come up with very complicated statistical models, hierarchical ones. We'll see a tiny bit of that in a minute. To what extent can we do that? What is the real landscape of statistical models? And if you'll let me dream for a minute, if probability is about reason, then this is about understanding what is reason, what is the scope of reason, what can we really discuss when we're thinking about probability. And the third one is more of an engineering thing, which you can quickly and easily prototype things with models. And this is again a bit of a dream. I think initially people thought we could have a probabilistic programming language where you could write a crazy thing, not know anything about simulation or statistics, give it to the simulation engine and it will give you the answer. So like millions of people could suddenly start writing really complicated statistical models, analyzing massive data. Okay, and that's, I mean, there's a spectrum of that, I think. So some of the languages Andy talked about, that's already the case, that you can have complicated models, fairly complicated models, easy to write, and fast simulation. But when we push to the extreme, it starts to become less clear that general simulation methods work and so on. So this is an interesting point. I mean, of course, if all you wanted to do was look at problems like this, you probably wouldn't want to do probabilistic programming. You'd probably want to make a specific library that would solve problems like this really quickly or whatever. Okay. So what I want to focus on then is general probabilistic programming, pushing it to the limit of having whatever general language we can with these three constructions. Okay, how long have we been going for? About half an hour. Shall we? Let me make this a little bit more interesting before we have a break, if that's okay. So, I said there were either 3 or 10. Oh, sorry. Before I do that, any questions about these three methods for understanding what programs do? Oh, yeah.
What do we know of likelihoods in the pairing cases?
Yeah.
Do we know them analytically or?
Yeah. Good point. Yeah. So how do I know the likelihood? Well, I look at analytically really. So I look at the formula for the Poisson distribution. Yeah. And I did 3 to the power minus 3 to the power 4 times e to the minus 3 over 4 factorial, and that gives me 0.17. Anyone do that in their heads quicker than me? And in this case, it's 10 to the 4 times e to the minus 10 over 10 factorial. Okay. That's this number here, and that's that number there. Okay. That's why they're not very pretty numbers, because they've got exponentials in and stuff. Yeah. Yep.
So how do you discretize the continuous PDF there?
Okay, the Poisson, that's a good question, but the Poisson density function is not continuous. It's only defined on integers. Yeah, so I don't need to discretize anything. Yeah. We'll talk about that in a second, though. Yeah, that's a good point. Yeah. Any more questions just now? Okay, so let's make the problem more interesting. I said that there were either there were 3 buses per hour at the weekend and 10 buses per hour on a weekday. Now, that's supposing I sort of looked it up on the city website, and it said there will be 3 buses per hour at the weekend and 10 buses per hour on a weekday. But suppose I didn't look it up on an official document. I just had a memory of roughly how many buses there were. I sort of remembered there being about 3 buses per hour on a weekend and 10 buses per hour on a weekday, but I'm not really sure. How could I incorporate that into the model? Okay, so what I'm going to do is change line 3. I'm going to change my observation. So change. Uncertainty about rate. Uncertainty about rate. We're going to change the program. I'm just going to change line 3 into 2 lines, actually. Firstly, I'm going to figure out what the actual rate is. That doesn't mean I'm going to ring the council and ask them what the actual rate is. I'm going to draw it from another distribution called a gamma distribution. We'll talk about that in a second. Where the mean is the rate that I think it is, but where there's some uncertainty. Gamma takes 2 parameters, but we'll just leave that one at 1. And then we make an observation. Then we observe the same thing. 4 from Poisson. Not with the rate I thought it was, 3 or 10, but with the actual rate. Okay. So just to show, so I don't really want to get into gamma distributions and stuff, but this is what a gamma distribution looks like. You can see it's a distribution on rates, well, on the positive reals. So when I said I thought it was about 3, well, it might be 3, but actually it might be a bit less. It might be a bit more. In fact, it could be anything, but it's probably 3. The average is that it's 3. When I said I thought the actual rate was about 10, well, it's probably 10, but it could be a bit less. It could be a bit more. It could be anything, in fact. And so I can incorporate that just by changing that line 3 of the program into this program. And I can then run that in my simulator. That's what I had before I changed it, and this is what I have afterwards. So when I add in that uncertainty, it happens that it makes it kind of equiprobable that it might be the weekend or it might not be. Okay, how does this affect our inference algorithms? Can anyone do the direct calculation now? Now my actual rate is gamma distributed. Okay. Well, you need to know something about the gamma distribution. I think you can probably do it if you're good at calculus and stuff, but it's much harder. So the direct calculation becomes much harder. We have to know quite a lot about these curves, integration, and stuff like that. What about the second method, Monte Carlo with rejection? That will work just as well, except rather than sampling n from a Poisson distribution, we'll first sample the actual rate from a gamma distribution. So there will be now 3 samples: sampling from Bernoulli, sampling from the gamma, and then sampling from the Poisson. And in the weighted Monte Carlo simulation, again, it's all fine. It's just that we'll have to now sample from a Bernoulli and then sample from a gamma to find out what the actual rate is. That's all okay. Now, when we sample from a gamma distribution, we don't just get true or false. We get any real number. So that's a bit interesting. Another interesting thing is that we never actually return the actual rate. When we return from the program, we just return whether it's the weekend or not. So when I calculate my posterior here, I've got no idea what the actual rate of buses was, whether it was the weekend or not. I've marginalized, statisticians would say I marginalized that. I didn't actually care what the actual rate was. I just wanted to know whether it was a weekday or not. So we have what's called a complicated now, well, it's called a hierarchical model, because the rate depends on the first thing, whether it's the weekend or not. And so you can imagine we could start making it even more complicated, where other things depend on other things, so on. Right, let's take a break now, and then I'll talk after the break about making it a tiny bit more complicated, and then I'm going to load up Emacs, and we'll have a look at how these examples actually run and how you can actually try using them. Okay. Oh, before we do that, any questions about the gamma example, I suppose? Yeah. Okay. So how long shall we break for? 5 minutes? 5 minutes. Back. Yeah. Okay, so we've been talking about this very simple probabilistic program where I looked out the window, tried to figure out what day it was by seeing some buses go past. And then we made it a little bit more complicated by saying maybe I didn't know exactly the usual rate of buses. I was just sort of guessing it. I just had some belief about it. Let me put that to one side for a second. And let's say instead of watching 4 buses in an hour, what kind of person looks out the window and counts how many buses go by in exactly an hour? Let's suppose I notice a 15-minute gap between 2 buses. How would I change my program? What I would do, so instead, changing observation. Observation. Let's say a 15-minute gap between buses. Now I said buses come independently, and so they form a Poisson process, and then the gaps between events or points in a Poisson process are exponentially distributed. That's another little thing to know. We'll put all this together, by the way, if we have time a little bit later in this lecture, to do with Poisson. But suppose we see a 15-minute gap between buses. Then we'll change line 3, let's call it line 3 prime, to observe 15 minutes. 15 minutes is 15 out of 60, which is quarter of an hour. Yeah. We observe 1/4 from, and that's a gap between buses, so from an exponential distribution, still with the same rate. Okay? I'm going to forget about the thing about the belief about the rate for now, so let's just keep it like this. So we know for sure that the rate of buses is either 3 or 10, and then we observe a 15-minute gap. Let's see what the exponential distribution looks like. People sometimes talk about exponential decay of particles and stuff, but it's also the distribution for gaps between things in a Poisson process. Okay. So how do we change our simulation? How do we change our calculations? What's the next one? So in the direct calculation, so it's going to give a different answer. It's a different observation. Don't worry, it's going to give a different answer. Can I change it in blue? Is that okay? So the prior probabilities are the same. I haven't changed line 1, but the likelihoods have changed. When the rate is 3, that's to say when it's the weekend, the likelihood is the value of the density function at that point, and that is 1.4. So this is with the 15-minute version in blue. So let's cross that out and put 1. What did I say? 1.4, and that gives us a different answer. A different unnormalized posterior probability, which is 0.405. Okay. And when it's not the weekend, there are 10 buses per hour, then the likelihood is the value of that density function, the exponential distribution with rate 10 at the observation point, which is quarter of an hour. And that point there on the y-axis is about 0.8. Okay. And the result of multiplying those two numbers together, someone do it in their head quicker than I walk across the platform, 0.586 is about there. Okay. So now we can go through, I don't know if I want to do all this, calculate the posterior by following through these numbers. So these numbers don't add together to give 1, right? So then an unnormalized posterior, we divide by the sum of them, and that gives us then a ratio of what probability it is that it's a weekday. It's not going to be 1.6 anymore. Let's move it. You can do, if you can't do that calculation, come and ask me afterwards. Okay. Yeah. What about Monte Carlo with rejection? Anybody spot any potential issues?
You've got a real value, so it's not easy to say quality.
Yeah. Yeah. Okay. Change this. Instead of sampling n from a Poisson, instead of sampling n from a Poisson, I'm going to sample the gap t from an exponential distribution with the rate. That's going to give me a time, which is a real number. And then I'm going to say if time is 0.25 is a quarter, then I'm okay. If it's not 0.25, it's not okay. What's the chance that my simulation is going to give me exactly 0.25? Zero. Okay? I'm just going to reject everything. That's not going to work. One way to get it to work is to say, rather than observing a quarter of an hour gap, maybe I observe 15 minutes plus or minus 1 minute. And then I could change this so that I say if n is, if t, so t is 0.5 plus or minus 1 out of 60, then it's okay, otherwise we reject it. And now it's going to still reject an awful lot, but it's not going to reject everything. Okay. By the way, that takes us to the meaning of the density function, which is, so here's the Poisson density function, looks something like this, and here's the quarter of an hour point. If I want to do quarter of an hour plus or minus epsilon, what's the probability of that? Well, that's that region. Here's the minus epsilon, and here's the plus epsilon. where epsilon's about 1 minute or something, the probability of seeing a gap of 15 plus or minus is the area under this curve, which will always be below 1. Okay. So the likelihood is 1.4, which is above 1, right? So it's definitely not a probability. There's no such thing as a probability of 1.4. A probability should always be below 1. But we can talk about a probability of something lying in a region, and then it'll be this area which is below 1. Now, what we could do is say, now put epsilon to get smaller and smaller and smaller and smaller, and in the limit, we'll end up with the right answer for the posterior. Okay? But that's not at all algorithmic, right? Because we'll end up rejecting more and more stuff as we make epsilon smaller and smaller. I wanted to say something else about this. I can't remember. Okay, let's talk about weighted simulation, see if that thought comes back to me. Oh, yes. This thing about the plus or minus epsilon only works because the density is a smooth function. Continuous function. Sometimes we'll have densities maybe that aren't continuous, and then it's not going to work. So who knows whether this is actually a good semantic definition. Okay, let's talk now about the weighted Monte Carlo method. So now we run the program k times, we sample x from a Bernoulli, and then we're going to weight the run by the likelihood. That need to change these numbers and where they came from. So that's going to be either 1.4 or 0.8. Okay? And then I go all the way through. I get pairs of true and a weight, or false and a weight. Those weights are going to be bigger than 1 sometimes. They're going to be either 1.4 or 0.8 in this case. So it might be bigger than 1, might be smaller than 1. Doesn't matter, because at the end we're going to sum it up and divide by the total weight, which won't go to 5 over 6. It will go to whatever the proper posterior probability of it being the weekend is. Okay. So weighted simulation works quite well. So for me, that's a good reference semantics. If you want or reference interpreter, interpreter for this language. So weighted semantics means we run the program some large number of times, sampling from whenever we see a prior, and weighting the run whenever we see an observation. And if the observation is continuous, as it is in this case with an exponential distribution, with a density function that might go above 1 or whatever, it doesn't matter, we just weight the run. We might end up weighting the run by enormous numbers or tiny numbers, doesn't matter. In the end, we get a sequence of pairs of a result and a weight. We add them together and figure out the ratio so the weighted ratio. How many things came out true compared to how many things came out once we include the weights. Okay. And that gives us a posterior probability. Okay. So, so that's what I wanted to say about simulation. So, as I said, one view on how to explain what programs do is by giving a reference sort of interpreter for them, a reference method for running them, and that's what I've been doing here. Tomorrow, I want to talk about giving us a more mathematical semantics to probabilistic programs. Okay. Sorry, I never showed you the answer. Sorry, this is the posterior thing, right? So it's about 0.4 that it's the weekend. Let's write that up. I don't think anyone was that interested in the actual answer. 0.4 when it was the weekend, and about, what's that, hang on, those numbers don't, 0.6 when it's, that it's a weekday, okay? So push that all the way through. 0.4. Well, that's assuming we get the epsilons right. Yeah. So for Monte Carlo with rejection, you have to, if you're going to have continuous distributions, we need real numbers, we need to be very careful, and maybe we shouldn't do it. Okay, so weighted simulation is the kind of reference implementation for me. Okay, you want to say anything else, Jim? No, let's talk now about some more examples and pushing things to become more and more interesting. Okay, so let's talk about a regression problem. Suppose I've got some points. Just keep it simple. Let's just have, 7 points? 1, 2, 3, 4, 5, 6, 7. And I want to know which function generated those points. If it was a linear regression problem, I want to know which line generated those points. Now, in traditional statistics, maybe you just find the line that fits them best. with least squares, the one that's closest to all 7 of the points. In Bayesian statistics, you're not interested necessarily in just the best fitting line, but what's the posterior probability that a line generated the points? So a distribution on lines given what the data points are. Okay. So in other words, we're going to talk about random functions. Let me show you then, let's before we do that, let's switch to look at the programs. Oh yeah, sorry, I should have done this first. This is the little programming language that I've been talking about. It sits inside Haskell. How many people used Haskell? Oh wow, yeah, more than, yeah. Okay. So in Haskell, those of you who haven't used it, Haskell uses monads, and this gives you a sort of a simple way of doing domain-specific languages embedded inside Haskell. So inside the do block, so Haskell is a pure language, but inside the do block, we're working inside a monad, and this monad has been set up so that it's really the language that we've been writing on the board so far. Okay. And so this is the program we first wrote with the buses and noticing noticing 4 buses out the window. I don't think I need to go through it even because it's exactly the same as what I wrote on the slide on the board, except I'm not using this observation syntax. Instead, I'm using the word score. So I'm going to be a little bit more intentional about this. Rather than saying I observe 4 from a Poisson distribution, I'm going to say, well, the Poisson PDF, we know, well, that's defined somewhere else, and I know what the rate is, and I know I've got 4, so that gives me the number, the weight, which is, I've rubbed it off now, whatever it was. Let's get it right. That'll be either 0.02 or 0.17, and then I return the result, okay? So it's a little language for describing, if you like, weighted Monte Carlo simulations. And it runs then inside a monad. Let me show you the monad just to... Very simple thing. I'll talk more about this tomorrow. But I've just got this little function called weighted samples that takes a program in the monad. I called the monad measure. We'll talk about measures tomorrow. And produces a stream of weights. It produces this stream of weights. This is just a Haskell thing that runs the program lots of times. That's what we said on the board informally. Runs the program lots of times, weighting the traces by the observations. Okay. So it's only, how many lines of code is that? Like 15 lines of code or something. That's the implementation of the language. Okay, so that's the first program. The second program we looked at was the thing where we weren't sure what the belief was. So I've written that like this. I sample the actual rate from a gamma distribution with the approximate rate as the average. Okay. So it's exactly what we wrote on the board. I think I've rubbed it off now. Oh no, it's up here. Yeah, exactly this, except I've changed it from writing observe to writing score. And then the third program we looked at, sorry, in the other order in the file here, is the one where we noticed a 15-minute gap, and it's exactly what I wrote on the board here. I just changed the third line to say observe a 15-minute gap. So what you can do is you can download I'll put a link for the zip file. You can download the zip file. Then if you run Haskell stack, then it will compile it for you, and you can start changing it and experimenting. Right, this isn't a professional tool. It's only about 60 lines of code or something. So it's not to the same standard as Stan or something like that. But I think because it's so short, you can easily experiment. Maybe try pushing different directions, seeing what works well and what doesn't when you extend the simulation engines. Okay, so let's switch now to, what was I just talking about? Regression. Yeah, let's talk about regression problems. Okay. So again, inside that monad, I've defined a little probabilistic program that's going to generate a random function. It's going to generate a random linear function. Let's do linear regression first, and we'll make it more interesting. So a linear function has a slope and an intercept, the point at which it crosses the y-axis. So I sample those from a Gaussian, from a normal distribution, that's a bell curve, around 0, standard deviation quite big, 3, so plus or minus 9 or something. Right? I don't really know what my slope is. I don't really know what my intercept is. And then I make a linear function, lambda x, ax plus b. And I return the function. So this produces a random function, a distribution over functions. I've not done any simulation yet, but let me show you what happens, or I haven't done any observations yet, but let me show you what happens when I sample from that. Okay? So I haven't tried to fit it. These are just maybe 500 samples from that prior, from the random linear functions. They're just a whole bunch of random linear functions. Look a bit like if you get some sticks and drop them. It doesn't look that uniform, perhaps, and there's some literature about how best to sample linear functions, but this will do for now. Okay. What I want to do now is to observe that one of those random functions generated the data points that I'm interested in, these 7 dots. Okay. So how do I do that? I've written a little function fit, which takes 2 arguments. The prior distribution, which is a random function, it might be the random linear function that we've just defined, or it might be a different one. It takes a stream of data points, that's those 7 points. Got them down here. Yep, the data points there, 7 points. And then it maps through all of them. So because it's embedded in Haskell, we can use all of Haskell's features, including map. Okay, remember, probabilistic programming is all of these 3 things from Bayes' law plus normal programming, and that's what makes it really powerful, I think. So we map across all of the data set this thing here. Now, we're not going to observe that the function exactly generated the data points, because there's no linear function that could possibly have generated all of these data points, because they're not collinear. So what we're going to do instead is we're going to suppose that we called that linear function, but then it was a noisy observation. So maybe there's some linear thing in the wild, but we go to measure it with our microscope or whatever, we get a noisy thing, we make mistakes. And we'll explain that noise. The standard way to do it in Bayesian statistics is using a Gaussian distribution, using a normal distribution. Okay. So we include that Gaussian noise by saying, I don't observe that fx equals y, I observe that I drew from the Gaussian with a very small standard deviation the number y. Okay. And now let me show you the result of plotting fit. So fit takes 2 arguments. It takes a random function and some data points. So I just called fit linear data. Linear is the random linear functions all over the place. Data is the 7 data points. And I just called fit linear data. Fit takes 2 arguments. This is what it gives us, a posterior distribution on linear functions. And I plotted those linear functions now. And you can see now the Bayesian regression idea is giving us, well, we could see maybe what the mean is. Yeah. But also we're not saying that other lines didn't generate those numbers. We're saying probably it was around here, but there's some small probability that it was a different line. If you want to have a go at programming, you could try, okay, what about fitting a cubic function? Set up a random cubic function. Cubic functions will have 4 parameters. Draw them randomly and then see if they'll fit to this posterior. Okay, let's make it more interesting and consider, let's consider a piecewise linear. So linear functions didn't fit these data points very well. Let's consider some other kinds of functions. So you could try cubics yourself. Let's talk about piecewise linear functions. Piecewise linear function to me means a linear function and then another linear function and then another linear function. Let's suppose I don't know where to choose different linear functions, where to piece them together. So in fact, I'm going to draw the change points from a Poisson process. A Poisson process is a random set of points. I can easily define a Poisson process in my system. Sorry, this is George's plotting stuff. So, yeah, okay. Here's a Poisson process. So it's a recursive function which is going to return a random list of points. And those are going to be the change points. But I'm not going to start with, it's just going to be a random list of points, identically distributed and independent. Okay. So I'm going to look at a particular window. So I look at the lower and upper. Those are the point. I want some points in between lower and upper. And I've got some average number of points in that interval. And the algorithm for drawing a Poisson process is you first sample from the exponential distribution. Remember, the gaps in a Poisson process are exponentially distributed. The gaps between buses, the gaps between change points, the gaps between whatever are exponentially distributed. So I draw from an exponential distribution and I get a gap. And then I'm going to keep going unless I've gone past the upper bound. And when I say keep going, I mean I draw the rest of the Poisson process and then I return the new point together with the rest of it. So it's a simple recursive function. It recurses because I call Poisson process again within itself. Okay. And let's see, I made a little video just to illustrate this. Okay. So these are some draws from the Poisson point process. So you can see there, they look kind of independent. They've got kind of a reasonable mean, but the number of points changes with each draw. How long is this video? Okay, it's nearly finished. Okay, so what we're going to do when we do our simulation is draw loads of lists of points and just try them all. Okay, so now I'm going to define a function splice, which takes a random function. That could be a random linear function that we talked about before with slope and intercept. Oh, sorry. It takes a random list of change points. That's going to come from the Poisson process, perhaps, or we could use a different process to generate our change points if we knew a bit more about where they were. A random function, that could be a random linear function, could be a random cubic function, random constant function, whatever. And it's going to give us a new random function which is spliced together at the change points. Okay, so I don't think I want to read this through. It's just really 90% Haskell gluing together the different lines. Okay, and when I do that, I end up something like this. So I call splice, and splice is expecting a random list of points. I'm going to get that from the Poisson process, these dots. And splice is expecting a random function. So I give it a random linear function. And now remember I had that function fit, which took a random function and some data points and produced a new random function condition on those data points. And I do that and I run a simulation and I get something like this. So what it's done is it's figured out the change point should probably be between 3 and 4 in this region here. Not quite sure where, but somewhere in that region. It's got some probability that it didn't want to change, actually. So that I don't know if you see, it's a bit faint, but there's a line going up here, which might have been the line that generated them. So it's a bimodal distribution on what the functions could have been that generated these points. Okay, you could go away, as I say, and have a go at, if you define a constant random function, you could just plug the word constant in there and run it again, you'll get a constant linear function, a piecewise constant function, or a cubic, or whatever. And let's make it even more interesting and say, maybe these, I can't actually remember where I got these points from. Maybe they came from a program that randomly generated them. Can we figure out which program generated these points? Okay. So let's do that. This is called program induction. Okay. Who here has written a little evaluator in Haskell before? Wow, okay. Well, did you do that in this course, or everybody just knows Haskell now? Okay. So I've got a little grammar. It's not a full like lambda calculus. Okay, just keep it a little bit simple. You can experiment, see how far you can push this later. A little grammar for Boolean for arithmetic expressions. It's got plus, times, negative. It's got numbers, all the real numbers in there, variables, and conditions as well. So we can have if then else inside our programs. And then the next thing that you do, maybe in your first year nowadays, you write an evaluation function which takes an expression, which is one of these trees. Okay, it's not concrete syntax, it's abstract syntax, but we can talk about that separately, and evaluates it at an argument. So if I've got an addition node, then I'm going to evaluate E1 at x and E2 at x, and then add together the results and go through. It sounds like you all know what to do here. Okay, conditional, I'm going to use. So this is a definition of interpreter. If you didn't know what definition of interpreter was, it's explaining what the arithmetic language means in terms of Haskell. Okay? In particular, my language construct condition is defined clearly in terms of Haskell's if then else. And now I'm going to define a random element of this grammar, okay, a random syntax tree. This is sometimes called a probabilistic context-free grammar. Okay. So the key thing is this PCFG, probabilistic context-free grammar of expressions. I don't know which expression to do. So I draw from a categorical. That's got nothing to do with category theory at all. Categorical distributions are just finite probability distributions. So I don't know, maybe 0.2 chance of having a binary operation, 0.1 chance of having a unary operation, so on. 0.01 chance, very unlikely I'll have a conditional. Okay. And then I'm going to build up a tree. So let's get a recursive function, because if I'm going to have an addition, let's say, I need to know what to put inside the addition, and so on. Okay. So it's a recursive function that randomly builds an expression. And now I can just straight away use it. I've still got that function fit, which takes a random function and some data and conditions the random function based on the data. And fmap, if you know what that does in Haskell, it just takes, so never mind if you don't. We take our evaluation function and we give it something from the context-free grammar. That's a random expression. When we evaluate a random expression, we get a random function. Okay? A random expression has one variable in this case. When we evaluate it, we get a random function which takes an argument and produces a result according to whatever that random expression was. So fit, then, we can give our random function that comes from our expression to the data, and it's going to find an expression for us that fits the data. In this case, I'm not sure what expression it's found, but it's a sort of maybe a quadratic function, x times x, because I've got multiplication in there. And then it's decided, even though it was unlikely, it's decided to put a conditional in there, and so on. Here's another draw, which I quite like. So it picks a, I don't know, maybe this is even cubic, or maybe it's quadratic as well, but it's quite a different one. And then it's put it's put an if then else. So if x is less than 3, then do this function. If x is greater than 3, do this function, something like that. Okay, and I've drawn about 10 things from it, and you can see it wasn't really sure where the change point, where the condition should be of the if then else. Okay. So these are all in the zip file that you can go ahead and download and play with. I'm not saying, that the implementation I have here, which is 20, 30 lines of Haskell, is the best way to do program induction. I think it's quite exciting that we could start to push in that direction. Just one little issue. The length of programs that we draw from this random expression is rubbish, right? So here's the length of programs that we typically draw. It's going to really focus on really short programs. Okay. And this is typical for probabilistic context programmers. Either you end up with really short things or things that are maybe infinitely long, which is also a major problem. So what I decided to do, in what I've shown you, the pictures I've shown you, is to include an observation. After I'd drawn my expression, I said, okay, actually I observe that the expression is 25 lines long. I can do that by just including an extra observe statement, extra score statement. And then I haven't plotted it, but then we see that the programs it's looking at are about 25 lines long. I put a big standard deviation there, so plus or minus 10 or something. And then it fits much more quickly. Okay. There's no way I could do this kind of thing with direct calculation. Yeah. This also illustrates another point, which is that the number of sample statements is changing each time. Okay. The number of, because for each branch in the context-free grammar I sample, and the length of my program changes, I'm using different numbers of samples. That's one aspect that's called non-parametric. We'll talk about that a bit more next time. But let's look at one last example before lunch, which is fun. So probabilistic programming is these three things from Bayes' law plus normal programming. Now in normal programming, we've got loads of libraries that people have already written. So here, people have written games libraries. They've written here, I've got a 2D physics simulator library. And we can just load that and use that as well as the three clauses of Bayes' law. Okay. So a little game, or I don't know if game is a bit strong, right? Here's a ball, which I'm going to drop, and I want it to land in the cup. I can put these bumpers wherever I like, at whatever angle I like. Where should I put them so that the ball lands in the cup when I drop it? Let's say I've got two bumpers. Where do I want to put the bumpers so that the ball lands in the cup? If I put them both over here, probably won't land in the cup. If I put them both over here, definitely won't land in the cup. Turns out, put them here, it will land in the cup. Now let me show you the program before we just see if it actually works. So this is all the program is. I just imported a 2D physics library, which is obviously not straightforward, but I don't have to worry about that. I don't have to worry about solving complex physics expressions when I do my direct calculation, because I just load the physics library. Okay, so what do? I need to know where my bumpers. Let's say there's two bumpers. So the Haskell has a replicate thing for doing things twice or however many times. Where should the bumper be? What should it be its x coordinate? What should be its y coordinate? And what should be its angle? I'm allowed to put bumpers at different angles. Okay. So I've got these three parameters for each bumper, x, y, and theta. And I'm just going to draw them uniformly. I don't know where they are, so I'm an uninformative thing to do. My belief is not there. I don't know where they are, so I just draw them uniformly somewhere inside the picture, which goes from -5 to 5 in both axes. And I don't know which angle, so I just go from 0 to 2 pi. Of course, that's a bit rubbish because it doesn't really matter whether you go all the way around or not. Okay, and then I try running the simulation. So there's a little function called try, which calls the 2D physics library with some bumpers. And at the end, we get back the position of the ball at the end. And then I want to observe that the ball's in the cup. So the cup is at the x-coordinate of the cup is 5, plus or minus a tiny bit. Now it's interesting, I didn't say the ball is actually in the cup. We'll talk a bit more about that next time. I just said the ball is approximately in the cup. Okay. So that's all there is to it to describe this model. And let's now see what happens when you run it. Oops. Yep. Oh, how do we get rid of this? There we go. You want to see another run? Another one? This one's a bit more interesting. A bit of a trick shot coming up here. You could do this all day. I think I've got 2 more. Okay. Oh, look at this one. Like that. Watch. Okay. So that maybe that gives you some idea of the power of probabilistic programming. What about? Okay, let me give you. So if you want to go away and have a go at this, what could you do? So what about? Oh, so those trick shots are a little bit. They're quite cool, but they're a bit cheating, right? If I actually dropped a ball and I'd put a line going like this, it's very unlikely that maybe I'd drop the ball slightly wrong or from a slightly different height, and it wouldn't then end up in the right place. So could you make it a little bit more robust by putting some noise in where the ball starts? I don't know exactly where the ball's going to start. Could you make it a bit more robust and say, okay, the bumpers, I might not be able to put them exactly in the right place. Maybe I'll put them slightly wrong, and then we want it to be robust under that. Could you put the cup further away so that we need more than 2 bumpers, and then figure out how many bumpers we need? So I haven't included the code for that, but I did this like here, and we can see some trajectories, right? So sometimes it's using an extra bumper up here and getting it in the cup. So in this example, I drew the number of bumpers from a Poisson distribution. So the positions of the bumpers became themselves a Poisson process. So with an unknown number. So it could, in principle, be an arbitrary large number of bumpers, but it's quite likely to be small. And we can do that. We can set a low rate and try and push it to get a small number of bumpers as possible. Okay. So, is there something else I wanted to say? Yeah, that's it. Okay. So some motivations for probabilistic programming. We're giving a meaning to statistical models. We've seen in this lecture a meaning based on sort of a definition of interpreter, weighted Monte Carlo, and in terms of simulation. What I'm going to do in the second lecture tomorrow is look at a more mathematical approach to giving a meaning based on measure theory. And so I'll explain that to you. You don't have to know anything about measure theory to understand that lecture, hopefully. We'll see about that. New ways of building new complex models. So we've started to see some models that... We started with models, I've rubbed it off now, but these models written in statistician's notation with a tilde. And now we've pushed it to models that involve physics simulations. We've pushed it to models with an unknown number of change points in our linear function, and things that start to push the boundaries of what you would traditionally write in a statistical model. I mean, we haven't quite gone past, I think, what a statistician would do yet, but we're starting to push there. And I'm going to go even further there on, what day is it? On Saturday. And then I've got 2 lectures tomorrow, if I've got it right. And in the first lecture, I'm going to talk a bit more about simulation. So weighted Monte Carlo simulation, well, it's a good reference semantics, but it's rubbish. Okay. So I'm going to talk about Metropolis-Hastings algorithm. I don't think Andy talked about Metropolis-Hastings, did he?
Nope.
No. So I'm going to talk about that tomorrow morning first. And we'll talk about how it applies to probabilistic programs, because it has a very natural fit, I think, with probabilistic programs. And my implementation of Metropolis-Hastings is about, as I said, 20 lines long or something like that. Okay, I wanted to ask you, how many people know, just to prepare for tomorrow a little bit, so a lot of you seem to know Haskell. How many people know about monads then? Yeah. Category theory? Okay, it's thinning out. Okay, I'll stop there. Okay. All right, measure theory? Yeah, okay. Oh, okay. All right. Okay, so we'll see you tomorrow for a bit more. Please do, one last thing. If you download this and you haven't used Haskell stack before, the first time you call stack build, even though my file is tiny, it will take an hour or 2 hours because it's going to recompile all of the Haskell libraries. Okay? So you might want to do that overnight or during a lecture or something like that. Okay, I'm not defending that, but that's how it is.